You tap checkout on an e-commerce app, the screen spins, freezes, and finally throws a generic error. In a modern stack, finding out why that checkout failed is like trying to trace a single drop of rain through a waterfall. 20 years ago, a website was one monolithic code base. A request came in, ran some database queries, and returned an answer. If it crashed, the server dumped a single clean stack trace showing the exact line of code that broke. Today, that single tap triggers a chain reaction. The API gateway calls the routing service, which calls the user auth service, which calls the cart service, which calls the inventory service, which calls the third party payment gateway. Each of these services is running on its own server, writing its own independent log files in its own format. When a checkout fails in the middle of that cascade, the stack trace dies the moment the request crosses the network. To find the bug, an engineer has to dig through 5 different log streams across 5 different clusters, trying to match timestamps that aren't even perfectly synchronized. You are completely blind. Distributed tracing is the technology that restores that site. It gives every request its own passport, stamped at every single border it crosses, reconstructing the entire journey from start to finish. This passport works using two simple abstractions: traces and spans. A trace represents the entire journey of a request, the complete end to end path from the user's initial tap to the final database write. A span, on the other hand, is a single unit of work within that journey, like a SQL query, an HTTP request, or a serialization step. Spans aren't just a flat list, they form a tree, a directed acyclic graph. The very first span, created when the user hits the gateway, is the root span. Every downstream call creates a child span to link them. Every single span carries three vital identifiers: a unique trace ID shared by the entire journey, its own unique span ID, and a parent span ID pointing to the span that triggered it. But for this to work, these IDs have to travel with the request. This mechanism is called context propagation. As the request moves through your system, the tracing library injects these IDs directly into the outgoing network packets. In the past, every vendor had their own headers, but today the industry has standardized on the W3C Trace Context. When a service makes an HTTP call, it adds a header called trace parent. It contains a version number, a 16-byte trace ID, an 8-byte parent span ID, and a trace flag. The receiving service extracts this header, reads the IDs, and immediately spawns a new child span using the incoming parent span ID. This context propagation doesn't stop at synchronous HTTP calls. When a service pushes a job onto an asynchronous message queue, it serializes the trace context into the message's metadata or properties. When a consumer pulls the job off the queue minutes later, it extracts the context, ensuring the trace continues seamlessly across time and space. So, how do these spans get collected? Your application code runs a lightweight tracing SDK, but if the SDK had to send every span directly to a storage database over the network, it would slow down your actual application. To prevent this, the SDK writes spans locally to a background daemon running on the same host, the collector. The collector's job is to offload tracing work from your CPU. It batches spans, compresses them, and sends them asynchronously to a telemetry pipeline, keeping your application's request path completely clean of telemetry overhead. From the collector, the spans flow into a buffer queue and then land in a durable storage database. Because tracing generates a massive volume of structured data, systems use highly optimized databases like ClickHouse, Elasticsearch, or Cassandra to index and search billions of spans instantly. Finally, a visualization engine like Jaeger, Zipkin, or OpenTelemetry's UI reads this storage. It reconstructs the parent-child relationships, rendering the trace as a timeline waterfall. Now, that failed checkout is no longer a mystery. You see a long red bar on the payment gateway span showing it timed out after 5 seconds, instantly pointing you to the exact root cause. But this visibility comes with a massive catch: volume. In a system handling 10,000 requests a second, tracing every single operation, including every database query and redis check, generates terabytes of data a day. The cost of storing your telemetry can quickly exceed the cost of running your actual application. To avoid bankruptcy, tracing systems use sampling. The simplest approach is head-based sampling. The moment a request enters the gateway, the system rolls a virtual die. If it lands on the sample rate, say 1%, the root span is flagged for tracing, and that flag propagates to all downstream child spans. The other 99% are silently ignored. Head-based sampling is lightweight and keeps costs low, but it is completely blind to anomalies. If a critical checkout error occurs only once in every 10,000 requests, a 1% head-based sample will almost certainly discard it, leaving you with no trace when you need it most. The fix for this is tail-based sampling. Instead of deciding at the start, the system collects and buffers all spans for every single trace in memory at the collector layer. Once the entire transaction is complete, the collector inspects the whole trace. If it contains an HTTP error status, an unhandled exception, or took longer than 2 seconds, the collector saves it. If it was a normal successful request, it is discarded. Tail based sampling guarantees you never miss a needle in the haystack, but it is technically complex and expensive. The collector has to buffer millions of active spans in memory, track when traces are done, and handle out of order spans that arrive late due to network latency. To keep engineers from getting locked into a single tracing vendor, the industry formed OpenTelemetry, a vendor neutral, open source standard for collecting traces, metrics, and logs. With OpenTelemetry, you write your instrumentation code once and you can swap your collector storage or visualizer backend with a single config change. None of this is free. Beyond the storage bills, distributed tracing adds CPU overhead to serialize headers and generate UUIDs. It also introduces security risks, as tracing headers can accidentally leak sensitive PII like auth tokens or customer emails into your centralized logs if not carefully scrubbed. So, when is all this overhead a mistake? If you are running a monolithic application or a simple 3-tier app where everything runs in one process, standard APM tools and local stack traces are all you need. Adding tracing would be introducing gold plated complexity to a problem you don't have. But the moment your system expands into microservices, serverless functions, or asynchronous event queues, you lose the luxury of a single cold stack. Distributed tracing is the thread that binds those fragments back together, ensuring that no matter how complex your system grows, you can always see exactly what it's doing. That's the architecture of modern system observability.